So, last class we have seen that how to solve a what is called optimization problem with constraint inequalities. Graphically we have seen how to solve it. Then in general we see if we have a unconstrained optimization problem is there, we know how to solve this analytically as well as the numerical techniques that we have discussed. So, in general if you have a problem optimization problem, and more specifically if it is a minimization problem subject to equality constraint and inequality constraint, first we can convert them into a unconstrained optimization problem by introducing some variables known as unspecified variables known as the Lagrangian multipliers. So, if you recollect this one, there are two methods. One method is the elimination methods, that this problem last class we have discussed, that suppose we have to minimize this function f, which is a function of x 1 and x 2, and it is given by this expression. Agree? It is quadratic form subject to, let us call it is a equality constraints. If you have a, here we have considered only one equality constant, then what we will do it, we will eliminate the variables. That means, in this expression x 2 is expressed in terms of x 1, agree, that taking this that side x 1, and then it is a function of x 1 only, x 2 is a function of x 1. So, I have written x f of x, which is a function of x 1 and x 2, now it is a function of x 1 only, agree, x 2 is replaced by f of x 1. So, this is the expression. So, now this equality constant is merged into a objective function or cost function. So, it is becoming a now unconstrained optimization problems. So, this problem we can solve it by using our standard technique, either analytical method or it is a numerical methods we can do. But this type of elimination process is not easy for variables more than or number of equality constraints. If it is more several equality constraints are there, then it is not a straightforward case. Even for two equality constraints, it becomes more tedious and complex. So, we can do only when that x 2 and x 3 we can express in terms of x 1 explicitly, then it is easy, but in most of the cases it is not possible. So, we have to look after for another alternative methods, and that method is called that you convert that set of equality constraint or inequality constraint, agree, into a what is called unconstrained. This equality constraint and inequality constraint will convert into a what is called inequality constraint, we convert into equality constraint, then the overall we will convert into a unconstrained optimization problems. So, let us see how to do that one. So, so that is called, basically it is a Lagrangian multiplier approach, Lagrange multiplier approach. So, our in general the optimization problem, constraint optimization problem is described like this way: minimize f of x, which is a function of x 1 x 2 dot dot x n, subject to equality constant h I x 1 x 2, in general it is a function of x n is equal to 0, and we have a how many equality constants are there? There are p equality constants are there, and that inequality constant g j, which is a function of x 1 x 2 dot dot x n, is less than equal to 0 for j is equal to 1 2 dot dot p. So, our problem is minimize this function subject to this type of equality and inequality constants. This is a m, not p, m. So, This problem first we have to convert into a what is called by unconstrained optimization problems. Once you convert into unconstrained optimization problem, then you can solve it by our different techniques, either numerical methods or the our what is called analytical methods. Let us see how we can formulate this one. So, this can I just mention you, if you recollect that if you have a inequality constants are there here, I can convert into a equality constant. Let us call you have a g of x, x is a function of this is less than equal to 0. Agree? So, that means that g of x which is less than 0, agree, with this one I have to add some variable. So, that the function g of x and that one will be a what is called 0. So, you can apply g of j x plus a positive term you add it x j square is equal to 0. When x j is equal to 0, that means it is equality constant of that one. It has a it may be g j of x may be equal to 0 or it will be a less than 0. When this has a some positive value, this indicates g j is less than 0. So, this inequality constant I can easily convert into a equality constant. This inequality constant I can convert into equality constant by adding what is called some variables s j square, where this term is always greater than equal to 0. So, this equality constant this is inequality constant, I will convert into a equality constant like this way, introducing some variable x j s j square. So, now, you see our problem is reformulated like this. So, this problem is reformulated like this way. The problem is reformulated, converting all inequality equality constant, agree, inequality constant is converted in inequality constant, and then we are putting this constant to the objective functions. The problem is reformulated as minimize a function L, new function we introduce, which is a function of x 1, x 2 dot x n, and we have a lambda 1, lambda 2 and lambda p, then you have a mu 1, mu 2. I will explain what is this mu 3 dot mu m, and there is a function s 1, s 2 dot s m. So, this function I will formulate by considering our original cost function or objective function. This is f of x 1, x 2 dot x n. Then this inequality constant, agree, if I put it here, that objective function will not change, this objective function value will not change when it reaches to the what is called the optimum conditions. So, I can write it lambda 1 h 1 x 1 x 2 dot x n plus lambda 2 h 2 x 1 x 2 dot x n. We have a such p equality constants. So, you can write dot plus lambda p h p x 1 x 2 dot x n. In addition to that, that inequality constant I have converted into equality constant. So, that can be also added to the our new objective functions, agree. So, that is mu 1 into that inequality constant, first inequality constant is converted into equality constant like this way, you see g 1 of x 1 x 2 dot x n plus s 1 square, this is, then mu 2 g 2 x 1 x 2 dot dot x n plus S 2 square, and so on. We have a m inequality constants, m inequality constants, which is converted into equality constant by adding S I or S j. So, this is m x 1 x 2 dot dot x n plus S m square. So, idea is that when this function has reached to the optimum value, it must satisfy this condition and this condition, which in turn it must satisfy these conditions. When it is this condition is satisfied, then this is 0. So, this 0 multiplied by lambda 1, 0 by multiplied by this. Similarly, this is also 0 multiplied by mu 1, 0 multiplied by this is 0. When it reaches to the optimum conditions, it must satisfy our conditions. That means, in a what is called it must satisfy our these conditions, agree. But when it is reached to the optimum value of these functions, that it must satisfy our equality and inequality constants. Now, this I can write it, if you see this is called, this L is called Lagrangian functions, Lagrangian function. So, new objective function is known the Lagrangian function, and lambda 1, lambda I, where I is equal to 1 to dot dot your p, and mu j, and j is equal to 1 to dot dot m. These are called the what is called Lagrange multipliers. These are called Lagrange multipliers. Agree? So, this and these values lambda I values always greater than unspecified. It is an unspecified value. It may be positive, negative and 0, unspecified value, and this mu I value is always greater than 0 for when you are minimizing the function of that L is greater than is non-negative. I will explain why it is non-negative, and this is the any value of, that means unspecified value. It may be positive, negative and 0. This thing I will discuss later. So, this is the new function. Now, you see what is our constraint optimization problem is there, that is converted into unconstrained optimization problems. Agree? So, one can write this expression, that is what is called Lagrangian function, by matrix and vector notation form. So, this notation one can write this thing into this notation form. So, lambda L, which is a function of x, is an n cross 1, function of lambda, which is a p cross 1, a function of mu, which is a m cross 1, and function of s, which is a, I will explain how you have defined lambda, mu and all these things, is equal to, I can write f of x, this is the f of x, if this is the f of x, then these are I am writing in vector form. So, it is a lambda transpose h of x, then lambda mu transpose, then g of x plus s square. So, this agree, where I am writing lambda is equal to lambda 1, lambda 2 dot dot lambda p transpose, and lambda dimension is 1 p cross 1. Similarly, mu dimensions is equal to mu 1 these are all Lagrange multipliers mu 1, mu 2 dot dot mu m transpose whose dimension is m cross 1. Similarly, this our S square, that S square, you see this one is nothing but a S 1 square, S 2 square plus dot dot S m square. Again transpose, this dimension is your again m cross 1. These are the things. And I told you this value of S, if you recollect this one, the value of S is here is a positive quantity, S square is a positive quantity. So, these are all greater than equal to 0. When it is equal to 0, that means G of S which is less than equal to 0, when S is S I or S 2 is 0, all these things, then it is the equality constant of G of x is satisfied. When it is greater than 0, then it is the inequality constant of G of x is G of j is satisfied. Agree? So, these are the things. Then where is h of x? So, we know what is lambda, mu and s. Agree? So, h of x is equal to your h 1 of x, or you write it h 1 of x, agree, h 1 of x, h 2 of x dot dot h p of x, agree. Or if, and then g of x is nothing but a g 1 of x, g 2 of x dot dot g m of x, and naturally this dimension is p cross 1, this dimension is m cross 1, and your s square dimension is like s 1 square, s 2 square dot dot s m square. This dimension is same as the g dimension, because we are adding with g s square. So, that inequality constant is converted into a equality constants. So, this dimension also m cross 1. So, keeping all these things in mind, that is our mu, all these things we have just mentioned it here. These are the all Lagrange multiplier, lambda and mu are the Lagrange multiplier, and these are unspecified, and these values are non-negative, that is we have specified. So, now once I got the what is called unconstrained optimization problem, that instead of minimizing f, now I am minimizing L, and we are embedded the our inequality constant and equality constant in the objective functions of that. So, then our question next is we can write it our what is called our KKT condition. Before that, that is called KKT means necessary conditions and sufficient condition in order to minimize these functions. So, this is called Lagrangian function, we want to minimize that one next our problem. So, next is before we discuss that one, we will just we have seen just now that if you have a x j of x is less than equal to 0, then we can convert into equality constant by using a variable s I s j square positive quantity, which will be this 0. When s is equal to 0, that means equality condition is satisfied. When s is not equal to 0 means positive quantity, that inequality condition is j of x is less than 0. When s j square is greater than 0. This is equality constant is satisfied when s j square is equal to 0. Okay. So, let us call, suppose if you have a some inequality constant like this way, let us call g 1 equality constant I am showing like this way, it is equal to x 1 and x 1 is greater than equal to 0. Then x 1 is our decision variable or design variables, agree, and that is given x 1 is greater than 0 means it is a side constraints is given, that x variable after doing the what is called optimizations minimization of the problem x cannot be negative, agree, non negative. So, this I can convert in our inequality type less than equal to 0, this one. How you can make it? This is nothing but a minus x 1, this indicates the x 1 is positive, agree, non negative this one. So, now if I put it minus of x 1, that will be less than equal to 0. So, now you see our G 1 is the inequality constant, which is our type, the type our type of inequality we have used less than equal to 0, this type I made it, agree. So, any inequality constant of this type I can convert into this time our Z type less than equal to. We have always written equality constant greater than equal to 0 and inequality constant of type of less than equal to 0. So, suppose you have a variable x 1 and that variable limit is given x 1 is less than equal to x 1 is greater than equal to a and less than equal to b. That means, x 1 has a lower and upper range or bound of x 1 is given. So, let us call this is g 1 of x, again this g 1 of x, not g 1, this is the bound it is given. So, I can this range I can split up into a two inequality constant. So, I can write it, if you see this one, I can write a minus, if you write it a minus x, if you write it a minus x, what will be this one? A minus x is less than equal to 0. Both side I minus again is both here minus x I mean subtracted minus x subtracted x 1. So, this I can consider is same as g 1 of x. Another constant I can write g 2 of x, I can write it that x 1 minus b is less than equal to 0. Okay. Now, naturally x 1 is greater than equal to a. So, if you just subtract a from x 1, then it will be less than equal to. So, this is one equality constant and this is another equality constant. If you have a range of decision variable or side variables range is there. So, that can be decomposed into two inequality constant of such type of inequality. Okay. So, this I mentioned you that before we discuss that our condition necessary condition, there is an important point is there to discuss the what is called KKT conditions. What is KKT we will discuss next. So, that is a regular point, regular points. So, regular point arise when equality constraints are present in the problem. So, regularly you can just write regular points arise when equality constraints are present in the problem, in the optimization problem. Now, you see if you have a regular point, the regular point has a two features. One feature is that if x star is the regular point, agree, and that regular point must be feasible. Feasible in the sense that it must satisfy the equality constraint and inequality constraint. This is the first feature of regular points. Next is that these regular points, agree, at the regular points you will get the what is called that equality constraints. Equality constraint will come from the problem statement, it is given equality constant and some of the equality constant will come from inequality constants. So, we can say the features there are how many equality constant we will get from the optimization problem. That means, equality constant will get h of x is equal to 0, that I is equal to 1 2 dot dot p. There are p equality constant, and there is a possibility is there, you if you have a x j of x is equal to 0 for j is equal to 1 2 dot dot small l. So, now our original problem was, if you see, j varies from 1 to, or you write it k, in place of this j, in order to make confusion, write k is equal to this. Again, our L is the, because our basic equation of inequality constant is x j of x is less than equal to 0 for j is equal to 1 2 dot dot small m. Out of this small m inequality constant of g j, we have a L equality constant of g of j. So, total we have a, because where you can say where L is less than m. So, if you see our original problem, we have a p equality constants, agree, and there are m inequality constant. Out of m equality constant of g, there is a small l equality constants. So, in all together, how many equality constants we got it? P plus small l. So, if you the point regular points, if the regular points that x star, if x star is the regular point, then it must satisfy that the gradient of that g, gradient of h and gradient of g k for equality constant, all these gradients should be linearly independent. Then that point will be the regular point of this optimization problems. So, now what is this? I just whatever just I mention it, I will just write it, so that you can. So, there are two essential features of a regular point. X star, whose dimension n cross 1. First point is this, that this regular point must satisfy is what is called all design constant. That means, it must satisfy all constant. The point x n cross n star, which is a regular point, if it is feasible, it must satisfy this what is called all constant. That means, must satisfy all equality and inequality constant, must satisfy all constants. This is one features. Next feature is that the gradient of the equality constant, gradient of equality constant, and what is the equality constant? Gradient g, gradient of h I of x, agree, and I is equal to 1 2 dot dot p, as well as bracket gradient of equality constant, equality, as well as the active inequality constant, that is gradient of g j of x, agree. This is the inequality constant, gradient of this, agree, for I is equal to 1 2 dot dot L, where L is less than m, agree. And what is the active constant? Active constant Active constraints are there for this value of x, for this value of x, if it is 0, that means constraint is more stringent, strict that conditions. So, when that means I is equal to 1, I is equal to 2, I is equal to dot L, this equal to 0, equality constants are there. So, this is called active inequality constants, this is called active inequality constants. Constraint for the inequality constants, agree, this is active. And inactive equality constants is which one? G I of x star, if it is less than 0, then it is called inactive inactive inequality constants. So, we have a gradient of equality as well as active inequality constant. Active inequality constant will come from the equality constants, agree, for I is equal to 1 to L, and here I is equal to 1 to P. So, these gradients, that means P plus L gradients of which satisfy these equality constants of the original constant equations, agree. If these gradients are linearly independent, then we will say that point x star is the regular point of the optimization problems. So, our is this constraints at these constraints, that is what you will learn, at x is equal to x star n plus 1, you see this the gradient of equality as well as active inequality constant for this at x is equal to this must form a linear independent set of vectors. If these vectors, that means in other words, if these vectors are linearly independent, agree, the equality constant and the what is called active inequality constant, that gradient of that vector is linearly independent, then we will say the x star is the independent, then x star x is equal to x star is a regular point for the optimization problem. Under considerations. Okay. So, this is the regular point. So, KKT condition starts with the x star is the regular point. That means, the equality all equality constants, agree, gradient of all equality constant involved in H I as well as involved in H G J active inequality constants, means when G j is equal to G j of x is equal to 0 at that point x star, if it is this set of vectors, that this set of gradients, that means gradients of these functions, if it is linearly independent, then we will call it is the regular point of the optimization problem under considerations. So, this can, because why is this required of that one, we will see later this one. So, KKT means karush kuhn taker, it is called KKT condition. It is nothing but a first is find the necessary condition for the unconstrained what is called constraint optimization problem, which is converted into unconstrained optimization problem using the Lagrangian multipliers, agree. For that function, find out the necessary conditions. So, let x star be a regular point. Now, regular point we understand. If you see our statement of the problem here, original problem, this for x is equal to x star, this condition must satisfy, because this is the regular all stationary points. You know how to find out the stationary points. All stationary points is not a regular point, but all regular points is a stationary points. Agree? So, if a regular point is there, that point must be in what is called feasible region, okay, or it is a design space, that x star must be in design space, because it must satisfy all these equality and inequality constant. Out of this, whichever satisfy the equality constant, we have a p equality constant, and out of this m inequality constant, there may be a small l equality constants may be there. So, these functions, if you find out the gradient of this function and that function at x is equal to x star, gradient of that function at x is equal to x star, what are the vectors you will get it, because this is a scalar. If you differentiate this one with respect to vector, then it is will get a vector. So, all these vector, if it is linearly independent, then I will call that x star is a regular point of the optimization problem under considerations. So, that is why it starts x is a regular point. Agree? X is a regular point of the feasible set. Of the feasible set means, if you put the value of x in the constant equation, it will satisfy the all constant, it must satisfy that one, then only if it does not satisfy at least one equality or inequality constant, that means our point does not lie in the design space or in the feasible space. So, that will not give you the answer of the concerned problem. So, this is and it is a local minimum agree, it is a local minimum for the function f, which is a function of n cross 1, subject to our constraint, subject to constraints s I h I x is equal to 0, I is equal to 1 to dot dot p, and g j of x is less than equal to 0, j is equal to 1 to dot dot m. So, this is the constraint. So, how to solve this one? We know Lagrangian function, how to form the Lagrangian function. First step, so that is the KKT conditions. What are the KKT? First step, form Lagrangian multiplier L. I am not, this L function of x, lambda, mu, that we have already discussed that one, and this is the s. This equal to, if you see this one, f of x plus summation of I is equal to 1 to p lambda I h I, all functions I am writing in terms of I summation, then this summation of j is equal to 1 to p, 1 to m, then mu j, agree, multiplied by g j of x plus s j square. So, this is the, and this is the case, and this is called Lagrange function. Agree? So, this function you have to optimize, means minimization. Our problem is minimize these functions. Okay? And we have written what is lambda, all these things we have written. So, we will not repeat this one. So, this is the equation this. So, our necessary condition is what? If you see the step 2, Lagrangian function we have made it, then step 2 is the necessary conditions, or to find the stationarity conditions, necessary conditions. If you see the way you are doing the unconstrained optimization problem solved, that means first find out the what is called necessary condition, that means gradient of their function assigned to 0. Now, you are writing. So, this now you differentiate this with so this is a function of x, x is how many component, n components are x 1 x 2 dot dot x n. Similarly, lambda 1 lambda 2 lambda n. You have to differentiate all these variable with L with respect to this mu 1 mu 2 dot dot this, and S is S 1 S 2 dot dot S m. So, this I am not writing repeatedly, dot is function of this one, and this is the function of x of k. X of k means k varies 1 to n. When you write k is equal to 1, I am differentiating the Lagrangian function with respect to x 1. So, if you do this one, see this, what you will get it that one, then both side you differentiate, both left hand side you differentiate the function with respect to x k, and k varies from 1 to dot dot n. So, this is the summation I is equal to 1 to n lambda I. I am differentiating with respect to x. So, lambda is a constant keeping other variables constant. So, I can write h of I x delta x k. Similarly, summation of that one, agree, j is equal to 1 to m, mu j is a constant quantity I can take, and now it is a function of that one only x, g is a function of x, other is not a function of x. So, you can write del of del x k, then this g, agree, that g j of x plus this term is not, will not come into the picture, or if you can write it, finally, it will not come into the picture this, and that must be assigned to 0. This is our necessary condition, but necessary condition is not complete. This is we have differentiated this thing k is equal to 1 to dot dot n variables are there, because we have a this L is a function of lambda also. So, again you will write it this equal to L this, then you can write it that function of this you differentiate with respect to lambda I, agree. And if you use this is the lambda I, see this one, lambda 1 into h 1, lambda 2 into h 2, lambda 3 into h 3. So, I am differentiating first with lambda 1. So, it will come h 1, then h 2, h 3 in this way. So, you will get it this h 1 of x, and that I varies 1 to dot dot p, agree. So, let us call this is equation number 2, this is equation number 2, this is equation number 3. So, you have differentiated with respect to lambda, then what is left with respect to this, with respect to mu j is equal to, now you see with respect to mu j, if you depend mu 1 I j is equal to 1, mu 1 j g 1 s 1 square. So, differentiate with respect to mu 1, other terms is not a function of mu. So, it will be a g j of x plus x j square g j of this equal to 0, because it is a necessary condition, if I assign gradient is assigned to 0. So, this is equal to 0. So, that j is equal to how many 1 to I j 1 to dot dot m, agree. Then you see this is the step 2, then you see step 3 feasibility check, step 3 feasibility check. Conditions. If S j square is greater than equal to 0, this implies g j of x, I have explained this in earlier also, is less than equal to 0, agree, and this is j is equal to 1 to dot dot m. When S j square is 0, then it is a equality constant is 0. When S j greater than 0 means positive, then this equality constant less than 0 is satisfied. So, this in general we can write it. So, we have given equation number 1, 2, 1, 2, 3, this is equation number 4, then you could give this is equation number 5, that is equation number 5. Then we can say that equation number 5, then step 4, because if you see this one, we have still left 1. That means, we have to do the find the partial differentiation of L with respect to S 1, S 2 dot dot S m. So, that is we called it is a switching conditions. Why it is a switching condition? You will see later that by clubbing that equation 4 and that I will write it switching conditions. Now, this condition is as this differentiation of this with respect to x j, because it is a function L is a function of s variables also. This you have to assign. Say if you differentiate this with respect to s mu 1 j is equal to mu 1 g 1 s 1 square. So, you have to differentiate with respect to s j. So, this is constant when you are differentiating with respect to j, only this term will be there. So, this differentiation will come twice mu j s j is equal to 0, that is j is equal to 1 2 dot dot m. So, let us call this is equation number 6. So, this equation I can write it, this is all are necessary condition, equation number step number 2, 3 and 4 equation. So, if you see the equation number 4, which is differentiation partial differentiation with respect to mu j, and step 5 or equation 6 partial differentiation of L Lagrangian function with respect to s. These two equation we can combine together and yields a resultant conditions 1. So, let us see that one what we can do. So, you multiply by both sides of this equation, that is this equation is mu j s j is equal to 0, both side multiply by s j. So, s j square is equal to 0. Agree? Now, recall this equation 4, recall this equation 4. Agree? If you from 4 we can write it this from 4 from equation 4 or recall equation 4, we if you see this one g j of x, that means, if you do the partial differentiation of L with respect to mu, I am getting that one as j square is equal to 0, multiplied by both sides the scalar quantity mu j. So, mu j g j, agree. So, mu j s j square is equal to 0, and this quantity is 0, you see from here this quantity is 0. So, you see we are merged these two equation, that is 4 and 6, which in turn that the equality constant of g j, which is converted into a equality constant that g j plus s square, these two conditions we have merged together. Actually, separately if you see del L of del s is equal to mu j s j is equal to 0, and if you see del L Lagrangian function with respect to mu j, that is we have seen that equation. So, this equation and this equation we have merged together, and ultimately we are getting this equal to mu j g j is equal to 0 for j is equal to 1 2 dot dot m. This is the conditions. Agree? So, what we will do from now onwards, if you want to solve this one, necessary condition you will write it del L with respect to x, del L with respect to lambda, del L with respect to what is called s and with respect to what is called mu, which merge together, I will write these conditions. So, this is the condition we have to write it, and this if you see, if I write this all this equality constraint, then I can write it mu 1 G 1, mu 2 G 2, mu 3 G 3 and dot dot mu what is called m G m is equal to, because each component is 0, is it not, individually just see. Then this I can write it, if you see, mu 1 mu 2 dot dot mu n m, this transpose, this is nothing but a, we can write it, it is G 1 G 2 dot dot G m, okay, and this equal to 0. This is a scalar quantity 1 cross 1. See here, this is a scalar quantity of 1.1. Again, so if you multiply by this, this is in vector form, we can write mu transpose G is equal to 0. So, this indicates that switching condition, it is nothing but a orthogonality conditions also we write it. This is the orthogonality conditions, orthogonality conditions. Agree? So, so now look at this, if you look carefully this one, this let us call I is equal to 1, G 1 G 2, G 1 mu 1 G 1 is equal to 0. There are two possibilities there, mu 1 and G 1 is 0. I can consider mu 1 is 0 when G 1 is not equal to 0, then this condition is satisfied. It can be also another conditions, may be G 1 is 0, but mu 1 is not equal to 0. So, if you have a what is called m such conditions, so how many possibilities are there to make these conditions zeros? So, if you have a 2 are there, let us call we have a 2, only 2 equations are there, 2 inequality conditions, one is this equal to 0 and this is equal to 0. I can consider mu 1 is 0 when G is not equal to 0, then this condition is satisfied, and I can consider G 1 is 0, but mu 1 is not 0. Similarly, here mu 2 is 0, but G 2 is not 0. When G 2 is not 0, it indicates it is a inactive conditions, means G 2 of x is less than 0, and maybe G 2 is 0 when mu 2 is not 0. So, if you have a such type of m conditions are there, in turn we will get 2 to the power of m conditions cases, 2 to the power of m cases we will get it, while we will solve the what is called that our what is called necessary conditions problems. Okay. So, next is last is your step 5, non-negativity of Lagrange multiplier for inequality constants, inequality bracket constants. Look at the beginning, that what is the we have just considered, that lambda is the Lagrange multiplier which was associated with the equality constants. If you see this one, our first slide, we have made a Lagrangian function where lambda or lambda 1, lambda 2 or lambda p all are associated with the equality constant, whereas mu 1, mu 2, mu 3, this is also Lagrangian multiplier, but they are associated with the inequality constant G 1. Okay. So, next is this one, mu j is greater than equal to 0 j is equal to 1 2 dot dot m. This will be true, this condition must satisfy when we are finding out the minimum value of the function, minimum value of function, and the this type of inequality is used, and for this is the non-negativity, or we can get it non-positivity, agree, non-positivity of Lagrange multiplier for inequality constants, that means mu j is less than 0 for I is equal to 1 2 this, when you will use minimum value of function, but type is greater than or equal to 0. Agree? Anyway, we will, this is the most general way, we will always will take less than or equal to 0, and last check is your step 6 is the regularity check. Regularity check, and regularity check, you know, once you find out that optimal point x star, then you check whether the all equality constants involved in the optimization problems, agree, whatever you got it, gradient of that one is linearly independent or not. If it is linearly independent, you can say that you are obtain the minimum value of the functions. So, you have to check gradients of active constants must be linearly independent. Means this is, you will see, for which j of x is equal to 0, j is equal to 1 2 dot dot l, and this is the active constants. It is a small n, not m. Out of m inequality constant, l equality constant is there. So, that gradient must be linearly independent. Okay. So, that in short, you know how to test the linearly independent test. If you have a set of vectors are there, let us call v 1, v 2 and v n, and that dimension of all this dimension is n cross 1. If alpha 1 v 1 plus alpha 2 v 2 plus alpha n v n is equal to this null vector this. If all the coefficients of associated with v 1 v 2 is equal to dot dot alpha n equal to 0, then it indicates, that means it indicates that set of vectors f 1 v 1 v 2 dot b n are linearly independent. If any one of this is non-zero, this indicates the set of vectors you can express a linear combination of these vectors, any vectors in a. So, then we will call the set of vectors are linearly dependent. So, next class we will just work out some problems and tell how to do, and also see the sufficient condition of the problems, necessary and necessary we have done. Next is sufficient condition. Thank you.